All right. Hi, my name is Cole Ellsworth.
I'm Dylan Libertor.
My name's Alyssa Hassman.
I'm Spencer Klein.
Today we're talking about the effect of carbon dioxide on oceanic environments and aquatic life.
Okay, to start off with just some of the impacts of rising CO2 levels. Some of the impacts on coral reefs specifically are coral bleaching, which can lead to decreased growth rates and overall weakening of coral reefs, which can impact island and coastal regions, leaving them more susceptible to flooding and harsher weather conditions. Some of the impacts to marine life include sensory impacts, which can cause fish and other aquatic life to not develop senses correctly, and also can increase mortality rates among marine life. So some of the basic chemical processes involved are atmospheric CO2 becoming aqueous CO2, and then becoming carbonate and bicarbonate, which can decrease the pH of water. Some of the rates of ocean acidification. The last time that the Earth experienced high CO2 levels that caused ocean acidification was approximately 35 million years ago. The ocean is usually pretty good about buffering these low pHs when atmospheric CO2 is at a constant. However, current CO2 levels are rising at an unprecedented rate, which leaves the buffers no room to balance out the pH. So to look back, about 55 million years ago, the Earth experienced very high CO2 levels during what was called the Paleoceanic thermal maximum, where the Earth saw an approximate increase in temperature of about 5 degrees Celsius. And then about 300 million years ago, there was a near disappearance of all coral reefs throughout the Earth. There's also been a couple of studies done about CO2 vents at the ocean floor, where fish and other marine life that live close to these CO2 vents have higher mortality or lower mortality rates, and they can't colonize nearly as well.
So before we look at the results, we kind of have to understand Le Chatelier's principle. So in order to understand the ocean acidification process, we must understand what Le Chatelier's principle says. And so the dictionary definition from Oxford principally states, a principle stating that if a constraint, such a change in pressure, temperature, or concentration of a reactant is applied to a system in equilibrium, the equilibrium will shift as to tend to counteract the effect of the constraint. So let's look at the diagram to better understand this. So per se, if we have more CO2, the balance will tip to the left. Thus, we need more carbonic acid, the H2CO3, to counteract it, so thus more H2CO3 will be added to the system to help balance out the equation, and vice versa. So looking at the involvement of chemical equilibriums in just natural ocean acidification, there's a bunch of different elements and compounds that are involved. Such compounds include carbonic acid, which is the H2CO3, your bicarbonate, which is the HCO3 minus, your carbonic or carbonate, CO3 2 minus, your calcium carbonate, which is just CaCO3, water, simple H2O, and carbon dioxide, CO2, with a few elements of hydrogen and calcium involved in the process. And just to kind of give a reference to people, carbonic acid is normally, that adds the bite in soda that we normally taste, but is primarily made when CO2 binds with the water, as seen in equation 2. And then bicarbonate is something that we normally found as baking soda, one of the primary compounds, but the difference with baking soda is that it has an Na plus or a sodium ion added to it. So, but still it's the same base that it's bounded to make baking soda. Carbonate is commonly used as a softener because it tends to bind to elements such as magnesium, and calcium, according to John Lazenby from the University of York in his study in 2016. And then calcium carbonate, this is commonly found in seashells. This is what makes up most seashells in the ocean. And so we're going to go deeper into our experiment that we have done to kind of show how it all works. So in part one of our experiment, there was the setup. So we took artificial seawater that we have made, and we put it into two 250 milliliter flasks, about 100 milliliters of artificial seawater. And then we massed and crushed 5 to 6 grams. Generally, it was more than, it was around 5.6 and 6 grams of seashell mass. And we put each sample into one of the 250 milliliter flasks. But one of the 250 milliliter flasks had a 20-minute carbon dioxide treatment from a CO2 tank to show the excess amount of CO2 in our environment currently. And then those were put on our electric stirrers for about a week. In part two, a week later, we separated the seashell mixture from the aqueous solution using dry filtration and dry separation. Through our gooch filters, we collected the seashell compound and left the aqueous solution that could be measured for its pH. And then we titrated to see the different amounts of carbonate and bicarbonate in the samples, and HCl was the titrant in that. Not that it's a big deal, but the concentrations of carbonate and bicarbonate and the pH were then calculated and are going to be reported here in a second after I get done with part 3, which is then we took those gooches and put those in an oven for a week to kind of get out any of the water, and then once we got out the water, those gooches were then dried and the masses were measured. Titrations were then done to determine the amounts of calcium and magnesium in the sample of the water this week. And then EDTA was the titrant for that. And then the concentrations of calcium and magnesium and the differences in gooch masses were calculated. So looking at the first part of our results, we're going to look at the t-tests. So a t-test is used to determine if two averages are different from one another. And for this experiment, a 95% confidence was used. So a 95% confidence basically means it can be said that either the two averages are statistically different or not statistically different. So if they are statistically different, the t-experiment will be larger than the t-table. But if the t-experiment is smaller than the t-table, it's not significantly different. As seen with the calculated 95% confidence intervals, the artificial seawater, our control, versus the non-carbonated, these two samples are not statistically different because the t-experiment is smaller than the t-table. But in the control versus the carbonated and the not carbonated versus the carbonated samples, the t-table is significantly different than the others by a large amount. And that's due to the fact that the concentrations of bicarbonate in the CO2 sample is 10 times higher than both the CO2 in the control and in the non-CO2.
Okay. As mentioned in part 2 of the experiment, the filtered solutions were collected and the pH of those solutions were then measured. The pH is just a measure of how acidic or basic a solution is. For example, as shown here in this picture, lemons are more acidic, so they have a lower pH, and things such as bleach have a higher pH because they're more basic. After the solutions were both measured against a control, which is the seawater that we used without anything done to it, the pH of the seawater that we measured was 8.06. The pH of the solution with no CO2 added was 7.8, and the pH of the solution with the carbon dioxide added was 7.17. As you can see, the solution with the carbon dioxide added was significantly lower than the pH of the seawater that we tested as our control. This is due to the fact that CO2 added into the atmosphere from vehicles, industry, all of those things, reacts with the seawater and produces carbonic acid, which lowers the pH as shown here. It gets more acidic. It lowers the pH of the water. In part 3 of the experiment, the masses of the original sample that we measured of the seashells that we put into sample were measured. The sample without the CO2 was 6.027 grams, and the sample with the CO2 was 5.701 grams. What this is saying is that in the sample with more CO2, more of the seashell material dissolved within solution over that week than it did without the CO2. The mass percent difference was calculated based off of the difference between the final solution and the initial solution, or the initial sample of the solids that we put into the solution. This percent is lower because there were lower, the amount of seashell in solution was lower in the end. The percent difference of the Ca2+ was lower in the sample without carbon dioxide because more of the sample was in its original seashell form than it was in the solution with the CO2.
So when we look at the involvement, again, of chemical equilibriums, going back to this slide, it's really simple. When more CO2 is added to the environment, it takes this Le Chatelier's principle. So when we look at CO2 gas being converted into its aqueous phase or into the water, CO2 combines with the H2O. Thus, when we have more CO2, we must balance the equation. So more H2CO3 will be made. And thus, as a result, if more H2CO3 is made in equation 2, then we look into equation 3, with a higher amount of H2CO3, more HCO3 will be made. HCO3 being made, more bicarbonate being made, will then cause more CO3 or carbonate to be made. Thus, as a result, there's a breakdown of CaCO3 because of the carbonic acid being in the water, thus breaking down Ca2+ and CO3. So it's a constant cycle of making the water more acidic and letting the shells not become or stay in their solid state, but making them become in an aqueous state.
Okay, so I know what you're all are thinking. You're there, why does any of this matter to me? I'm just here because I want to see the Great Barrier Reef and I just want to look at all the fish. Well, in fact, the increased CO2 in the atmosphere has a direct relationship with the Great Barrier Reef. As I mentioned before, the ocean water is becoming more acidic due to the increase in carbonic acid. What this means is that it's increasing the corrosiveness of the ocean, which is in turn destroying some of the wildlife that is within the ocean itself. This is dissolving the seashells of infant crustaceans such as lobsters, oysters, mussels, things like that. It dissolves them when they're infants so they're not able to reach adulthood because they don't have that form of protection that they normally would have if there was less CO2 in the atmosphere. This is also disturbing the coral reefs. So as the acidicness of the ocean increases, it's dissolving some of the coral and the sponges and everything that's down in the coral reef. Most of the wildlife in oceans feed from the coral reef, or they feed off animals that feed off the coral reef. So in turn, the destruction of coral reef is potentially will be the potential destruction of the entire ocean ecosystem as a whole. So in a couple years or a couple hundred years, maybe there won't be a Great Barrier Reef to even look at. And this destruction of the coral reef will also ruin the marine food web, because as littler things start to not be able to feed off of the coral, the bigger things can't feed off the little things, and then we don't have food and there's no organisms left to survive.
And as Alyssa has mentioned, the mollusks as well as the corals will be affected heavily by this, with the removal of carbonate from their actual seashells. Seen in the bottom image, that a sea butterfly shell was put in a solution with a lot more added CO2, and after exposure, it started to break down in order to keep the Le Chatelier's principle going, trying to balance out that carbon dioxide. Another thing going to be affected is something known as phytoplankton. Now, contrary to popular belief, trees don't produce the most oxygen on this planet. What does are these little microscopic plants in the ocean called phytoplankton. Some species will thrive in a carbon dioxide-rich environment, while others will die out. They primarily feed on carbon dioxide to produce oxygen, However, their rates of devouring this will differ, and some will just straight out compete some other species, starving them, or they just can't keep up with how much is in there, and it just becomes detrimental to them. In a study that was done by Dr. Stephanie Dutkiewicz and Mick Follows, there's 4 major groups that they have determined, and Dr. Dutkiewicz is a research scientist at MIT's Center of Global Change, while Follows is an assistant professor at MIT's Department of Earth, Atmospheric, and Planetary Sciences. One direct quote from Dutkiewicz in their study was, "Generally, a polar bear eats things that start feeding on diatoms, and is probably not going to feed, not fed by something that feeds on Prochlorococcus, for example." Now, big words there. The simple part is that the polar bear may feed on a species that feeds on one species of phytoplankton, but not the other. If the one species disappears, the direct predator to that will start starving and dying off, and it is felt all the way up the food web, up until the apex predators, the polar bears, and that also includes us, since a lot of our diets consist of fish, or some people are completely pescatarian or eat only fish, no meats. And so bottom line is, we are affected by this as well. How are we affected? Taking just a look at cairns, just right here, right off the Great Barrier Reef, job losses from dwindling local fish markets. There's not going to be as many fish here, as they're all starving, dying off, or dying from the rapid pH change. Diets would be altered significantly for people such as pescatarians, also as well as island nations such as Hawaii and Japan. Japan specifically, basically, it just eats straight fish due to their small volume. They don't really have a lot of room for agriculture, so everything they eat comes from their surroundings, and in this case is the ocean. There would be a lot more migration into the cities, and urban sprawl would happen, cities going out further in order to make up for this, which would most likely not be able to be sustainable. Fisheries themselves, mollusk fisheries would be hindered as their payloads shrink, as well as the mollusk's shells are shrinking to non-existence. Actually, these fisheries are also already feeling this effect. As mentioned, the island nations, their diets are going to be upheaved with this as well. And humans in general, those phytoplankton I mentioned earlier, that produce 50 to 85% of Earth's oxygen, some of those are not going to make it. Now, how do we address this problem? What causes the problem we're seeing? And you could probably already think, well, are you telling us to stop burning our fossil fuels, our cars and all that? That's not the answer. Burning less fossil fuels is not enough. It's a start, but it's definitely not enough. Livestock farming also produces some of these greenhouse gases that does speed up this process as well. Deforestation is actually pretty much 2 or 3 bladed sword, where you're burning fossil fuels to power vehicles. You're destroying the wood, which if by burning also produces a bunch of carbon dioxide, as well as you're destroying a method of producing oxygen. The best way for civilians to help deter this is the good old carbon footprint. For instance, because of the livestock farming issue, eating less meat, if you do the Meatless Mondays, that will help cut down on livestock farming, as just cutting that down in general. Carpooling, again with that, traveling less. Reducing plastic usage as well. Plastic takes a lot of fuel to create the bags and the cups as well. One instance of even saving you guys money, instead of whenever you go to restaurants or going to get refills and getting the plastic cups and straws, if you were to buy your own refillable, you would most likely be saving several dollars each trip you get to get drinks. And that would also cut down on the waste going towards the environment, as well as reducing how much plastic is being used that will never break down. Recycling is also great as well. Pushing companies to make plastics that are recyclable. Going back to the reducing plastic usage, you're just keeping it cycling within itself, and it would be fine with that. The biggest thing though is make it enemy number one. Currently, the kitchen table talk is all about climate change. Well, climate change has an evil twin, and it is ocean acidification. It is an unsung evil that needs to be spoken of as well. The best way to do this is educate on the topic, shift topics from just carbon emissions, from just climate change, to include carbon pollution solutions, and a lot of these will come to light as well. The biggest problem is not many people know about ocean acidification. Only those in the field know about it and are trying to respond to it. If it becomes a more known threat, people will start reacting to it. Now, the experts on the matter, what are they doing to try and help? From what has been seen with most studies, research. The future when it comes to an acidic ocean is unknown. There is a lot of speculation, but what has been found is similar with the National Resource Defense Council, where they straight up just say, it is unknown what is to come, and they need more research and more monitoring, which would also include more funds so that they can do this. They had published 2 studies that identified communities that show people at risk of ocean acidification. In the National Climate Change magazine in February of 2015, there was 15 U.S. coastal communities that would be affected. The other study shows countries heavily affected by both ocean acidification as well as global warming or climate change. Another expert in the field, Dr. Robert Dunbar. He's a professor of environmental Earth system science at Stanford, and he actually did a TED Talk where he explains that current regulations of carbon dioxide is more of which engineered for terrestrial life. It does not take into effect what it's doing to the ocean, and the overall consensus is there's too much. There's too much carbon dioxide. It's thought of that for terrestrial life, how much is fine, but terrestrial life is also more adaptable for that carbon dioxide. The marine life is not. Other findings, and is pretty much just research and monitoring, such as from the National Oceanic and Atmospheric Administration, their ocean acidification program. If you visit their page, it's basically just lists of research and monitoring, as well as the Woods Hole Oceanographic Institute. Now, with this problem, coastal communities such as Cairns itself, as well as any other coastal communities, island nations, if this goes full circle and it reaches its end, there's going to be a lot of devastating reactions. Without the Great Barrier Reef, which it is very possible through ocean acidification, it could die. Without that, without the Great Barrier Reef, their fisheries, their local economy, as you guys, the tourists, help with this as well. You guys would not be here if it were not for the Great Barrier Reef. Their local economy would be devastated heavily, if not completely collapsed, as well as many other tourist destinations and anybody else that lives off of coral reefs, the ocean itself, or anything that is related to the ocean, which, if we have explained by now, is pretty much everything. We do ask you to take this seriously, as something wicked this way does come.